Hello, everyone. Welcome to the July 2021 meeting of the Naperville Astronomical Association. Thank you for joining tonight. A few upcoming events. So on Tuesday, July 20th at 7:30 p.m., we're going to do an Astronomy Fundamentals program. It's kind of a kids question and answers. We had some kids send in videos of them asking questions, and we're going to try to answer them. This will be the last program that we do on Facebook Live, because in August, the August 3rd meeting, will be back in person at the Naperville Municipal Center. The one big change, though, is it's going to be at 7 p.m. instead of 7:30. The Municipal Center changed their kind of hours of operation, so they end. We have to be out of there by 8:30, which means we need to start our meeting a little bit early. The room will be available at 6:30, so if you want to show up a little early and talk to some people that you haven't seen in a year, feel free to do that. But we will be starting at 7 on the dot. And Bill Higgins, who's a member of the NAA, will be presenting on the Mars Perseverance rover. And if you can't make that meeting, we do plan on recording that and posting that within a couple days on our YouTube channel. Also, in August, we plan on doing outreach again. So it's been a long time, but we plan on having our Riverwalk events again, and then public events at the observatory should start back up, weather permitting. And you can see all these events as we start populating our calendar again at neighborastro.org/calendar. So this evening, if you have any questions, please post them in the comment section on Facebook, and we will be monitoring that. Or you can email questions@neighborastro.org, and we'll be watching that email account, and we will feed those questions into our speaker, and she will try to answer those live for you if they're pertaining to her presentation. So this evening, Dr. Pamela Gay will be talking to us about rethinking water worlds. I'm going to turn the floor over to her right now, if you are ready.
Hello, good evening, everyone. I have to admit, I'm a bit harried this evening. We had a bird in the house, and I have 3 herding dogs, and there was much excitement, much barking, and the bird was eventually caught with a very large fish net. But this was not something I expected to be doing prior to this talk. So please bear with me in my slightly harried opinion. There were also running up and down of many stairwells involved. Anyways, right now I am wishing I could dive into one of the many water worlds that we will be discussing this evening. And I'd like to start by just contemplating our entire solar system for a moment. I think most of us, when we were kids, were taught that Earth, the pale blue dot, we are the one and only water world in our solar system. We were taught Moon, desert, Mars, desert. Other worlds, gassy, icy. Mercury, boiling. Venus, worse. It's acidic and super hot. In general, this was not the kind of place where we really thought there would be the kinds of resources that you expect to need for life pretty much anywhere but here, which makes here a pretty good place to be. But scientifically, we're always interested in everything out there at the edge of the solar system, beyond what we can easily see, what we can easily visit. We want to know the things that are the hardest things to know. And back in the early 2000s, we launched a little spacecraft called New Horizons on a giant rocket. And that giant rocket took it straight beyond the Earth's orbit, launched it straight on a trajectory to become the fastest moving object in our solar system as it headed out for a fast flyby of the worlds Pluto and Charon. And what we saw was nothing like what we expected. We expected Pluto in many ways to look a lot like Mercury, an extremely battered world that was covered in craters and maybe icy, we didn't know, but definitely desolate. What we found instead is this world that literally appears to have a heart, or at least a heart-shaped structure that was on the near side of what the spacecraft was able to see. One of the unfortunate parts of this mission is because it was a flyby, we were only able to get high-resolution images of one side of either of these worlds as the spacecraft went full tilt boogie on its way out of the solar system past Pluto. Now, the thing is, as New Horizons approached Pluto, it was able to get lower resolution images at a greater distance of all the other parts of this classic planet. And in processing these images, new techniques have allowed researchers to realize that while the front side of Pluto, relative to where the spacecraft was at closest approach, has a heart, the exact opposite side of Pluto, the side that unfortunately we only got lower resolution data of, it appears to have its own tiger stripes, its own chaotic terrain. And in trying to explain this dichotomy between the two sides, it was realized you can kind of get a shape like what we see for the heart if Pluto experiences a terrible impact. Now, if that impact occurs, it will melt a region of the surface, and it will send shock waves all the way around the world, where they will come together and interfere on the other side, creating this chaotic terrain. And exactly how Pluto is put together, how much of it is a solid core, how much of it is perhaps a liquid ocean, how much of it is an icy surface. All these things have to be factored in if you want to recreate that chaotic terrain from an impact. And this is exactly what graduate student Adine Denton recently did. She went through and she ran hundreds of computer models, looking at different depths of liquid water beneath a tens of kilometers thick icy surface with a solid core. And what she found is there is likely an ocean so thick beneath the surface of this ice that if that liquid ocean has life, there is a greater habitable region inside of Pluto, if you count liquid water as what you need to be habitable. There is likely a greater habitable volume inside Pluto than we have on top of our own world when you factor in all the oceans and assume that life exists in general within 10 kilometers of the surface of the planet up or down. There's error bars involved, but within error, the volume of ocean is the same as the volume of habitable area here on Earth. And that volume of water is a whole lot bigger than what we have. And this is starting to make us realize we have more surface water than anybody else, but we're actually a pretty dry world as far as we know. There could be water inside the mantle, but based on our current understanding, Pluto's got more water than we do. And this seems to be a common factor out in the Kuiper Belt. This is a picture of Triton taken by a Voyager spacecraft. And Triton is larger than Pluto. And had it not gotten, unfortunately, too close to Neptune in its orbiting of the outer solar system, it probably would have been accused of being a planet at some point in its past. Now, with Triton, when we look at it today, we see it in a fairly circular orbit, and we know that that isn't how it all started. Once upon a time, long, long ago, Triton was orbiting a lot like Pluto, except it didn't stay out of Neptune's way. And because of this, at some point, the planet had the Kuiper Belt object go a little bit too close, and it ended up swinging into what would have initially been a highly elliptical orbit. Now, over time, tidal effects, where when the world was closer, it was squished, and when the world was further away, it was able to spring back out. That tidal flexing of the entire world would have generated heat. And the heat got rid of energy in the system and allowed its orbit to evolve. Now, the question becomes, how much was it able to melt? And we can actually start to get at it by looking at today's structure, just not with the data we have. And this is where there had been a mission proposed, Trident, to go to Triton, that was in competition with Da Vinci and Veritas to go to Venus. There was a competition of multiple missions. And Trident would have had the ability to take high resolution images of this entire world to figure out, did it once become a liquid ocean on the surface that re-solidified from the surface down? Or did it not actually melt all the way through? Now, the reason that we can do this just by imaging the world is because we have figured out that things take on different structures, have different sharpness in their structures, depending on how they melt. Think of it this way. If you have an ice cream scoop and you set it on a cold plate on a hot day in a sunbeam, it's going to lose its structure and melt from the surface out. But if instead you take that ice cream and you put it on top of a hot piece of pie in a cold room, it's going to slough out and melt from the bottom up. Now, however it melted, it got refrozen. And we can start to decouple what order and how much melting occurred with high resolution images that we don't have. But from what we do have, we can tell that this is a world that is at a certain level active. There are cracks in the surface that indicate faulting. There aren't a large number of craters, which indicate the surface is getting redone on a fairly regular basis. This world doesn't have lava to recoat it. It has water. It's getting resurfaced somehow through melted liquids getting out to the surface and changing the surface. World after world allows us to see these weird tectonic features where instead of having magma and mantle interacting like we have on Earth, we have liquid oceans and icy surface layers interacting. And the kinds of features we get are truly amazing. This is Enceladus, one of the moons of Saturn. And Enceladus has these features that are, again, called tiger stripes. These are the OG tiger stripes, if you want to be one of the cool kids. And what's happened here is we once again have a world that has ended up with non-symmetric ice because of how it gets flexed as it goes around and around Saturn. It has built up thicker ice at the equator and thinner ice at the poles. And once upon a time, before we had all of these cracks, there was a day that it went from having a mostly solid surface to the ice was thinner in the northern hemisphere and the southern hemisphere, and something had to give. And it turned out that it was in the southern hemisphere that it gave, and one crack developed. And out of that one crack, this rotating moon began to geyser fluids that froze and resettled down onto the surface. And because the world was rotating, You'd have stuff come out of the crack. I'm doing this too fast. Stuff come out of the crack and then land a partial turn down onto the surface. And it built up and it built up. The ice there was thin. And the pressure inside was great from all of the heat generated from tidal effects of Saturn. And the ice cracked open. And now you have two places that are geysering up as it rotates. And now the stuff is falling down. And eventually a third crack opened under that third pile of falling material. And then a fourth crack. And at the fourth crack, the world finally had started to hit an equilibrium where the amount of stuff being expelled wasn't really enough to re-crack the ice further away. But it was enough that the crack stayed open. And Cassini was able to see the expulsion of materials geysering out of Enceladus during its orbit. Again, we have a water world. And this isn't one that we had expected. The orbit of Enceladus is circular enough we didn't think it would be this dynamic. Turns out a lot of our assumptions are overly conservative. We all grew up thinking we lived somewhere special, thinking we lived somewhere that was more interesting. And it turns out every world is amazing in its own unique ways that scientifically make perfect sense. Looking from moon to moon to moon in the Jupiter system, here we have Callista, sorry, not Callista, Io, Callista, Ganymede, and I just forgot the name of the other one. You're going to have to forgive me. Sorry, it was Europa. Io, Europa. It's a day. I caught a bird. Io, Europa, Ganymede, Callista. These four Galilean moons each have their own liquid on the inside. And one interesting thing I recently learned is Io, that sulfur-colored world that is constantly resurfacing itself. It is dynamically treated the same way you treat a liquid-filled world. Or, put another way, a liquid-filled world is treated the same way you treat a magma-filled world. The physics is the same. It's the viscosity that changes. And what we're realizing is, well, poor Io is an artistic form of hell. Each of these other worlds have subsurface oceans of their own. Europa, uniquely, the world that we were told all worlds belong to you, but this is actually the most likely place to support life in our solar system. It generates heat through tidal effects. This is something that we're going to keep saying over and over today. Again, all that I mean when I say tidal effects is when it gets closer to the world, it gets squished a bit. Or in this case, when it gets between Jupiter and another moon, it will get stretched and then it will rebound. So different effects cause its core to constantly change. That generates heat. That heat liquefies the water around it and drives changes in the surface ice, drives movements. And this world has an ocean that is many times deeper than our own, many times larger than our own. And what we now know, thanks to the Mariana Trench, is with Europa, there is likely deep sea hydrothermal vents. And those hydrothermal vents are capable of supporting life that doesn't need sunlight. When we were kids, most of us, we were taught that life required 3, maybe 4 things. It required water. Well, that got upgraded to life requires a solvent. We'll get to that in a moment. We have been taught that life requires food. Well, what it really requires is nutrients, and those can actually be gotten from rocks. Life requires companionship, maybe. That's that fourth maybe. And life requires a thermal gradient. That's something we don't normally think about, but it turns out that's one of those things that life really needs. You can't exist with everything at exactly one temperature because then you don't have any chemical reactions. So you need some sort of thermal gradient. Deep sea vents provide that nutrient, provide that energy. They have that solvent, they have that energy gradient. We don't know if they have companionship. We don't know how easy or hard it is for life to form. What we do know is everywhere we've gone looking for life here on Earth, and we've looked at more than a bucket full of sand, we've found life. There are some areas where you have to look at a bigger bucket full of whatever, but everywhere we look, the bottoms of mines, the bottoms of oceans, under ice caps, and even in pools of radioactive material, we find life. Ganymede and Callisto are both also thought to have subsurface pockets of water. We don't know if they're ocean worlds, but they could be. In putting together this presentation, I realized there is going to be the ability within our own solar system to start to get at one of the variables in the Drake equation. How readily does life form? Because we have so many places to go look. If it's rare, we may not find anything anywhere else in our solar system. If it's easy for life to form, we could find life everywhere. And the most tantalizing place for us to look right now is Mars. This is Jezreel Crater. And this is where Perseverance rover and Ingenuity helicopter are currently exploring. Well, to be fair, mostly Perseverance is sitting there waiting for Ingenuity to finish doing all the things it's going to do, because Ingenuity doesn't have enough power to communicate back to Earth all by itself and can only travel so far. And they have Ingenuity flying over things that are too hazardous for Perseverance to rove across. And when they're done, then these two will travel like two animals in a Disney buddy movie across the surface of Mars. And the reason that they were sent to Jezreel Crater is this is an area that we believe is a river delta, where water at some point crashed into this crater and filled the floor, streaming in, reshaping the structures. And with Perseverance, they have the capacity to take a number of samples, which Percy will then continue to carry along in a special container in the belly. And eventually, Percy is going to lay like a cache of scientific eggs, all those little samples of surface. And it's hoped that sometime in the 2030s, another combination of rover and rocket will land, and that future rover will collect up all those eggs of data, carry them back to that rocket, and send them back to us to explore here on Earth. And expect similar things here. And there's always that amazing possibility that the rover will be able to see something that looks like what's called a stromatolite. These are rocks that formed through the buildup of mats of algae over perhaps centuries, perhaps millennia, that as the algae died off, it eventually solidified into stone. We see these in some of the oldest places in Canada and Australia, which is the oldest parts of our world's surface. And we've previously seen things that looked like stromatolites on Mars, but we didn't have the capacity to go up and take a sample that we could send back to a power-hungry lab on Earth. And this is the real frustration that we have. Curiosity and Perseverance are built on a similar chassis, so think of them maybe as updates to the same model of a car. They have the same basic frame, but what's mounted is different. And neither of them have a whole lot of electrical function. This means that as much science as we may want to do, we are limited in how much power that microscope needs, how much power that mass spec needs. A regular police laboratory uses 10 to hundreds of times the electricity of Curiosity and Perseverance. So we need to bring those samples back here, where simply put, we have more electricity to burn, and where we can see what chemistry the water that used to exist on Mars allowed to happen. And it's in trying to understand the history of water that we find some of the most exciting structures in our solar system. This is Ceres, the largest of the asteroids, the original former planet. It was the first asteroid to be found and was considered a planet for a couple of decades before it got demoted by anyone. And it actually, for some people, stayed a planet longer than the IAU considered Pluto to be a planet. Ceres, as the Dawn spacecraft approached it, was discovered to have these shiny spots. And these shiny spots got everyone's attention because we were not expecting to literally find shinies on the surface of Ceres. And in one of my favorite spacecraft images, this is an actual image that has totally been enhanced and stretched. All you astrophotographers out there know what I'm talking about. But this is an image. And what it's showing is a strange, we think, cryovolcano in the bottom of a crater on Ceres. And it's thought that at the bottom of the crater, the crust is just a little bit thinner. And a salty, briny ocean beneath was able to well up and form a cryovolcano that erupted with salty water. And as that salt settled back down onto the surface and the water part sublimated away, what was left is literally a salt-covered volcano, not too different from volcanoes we see on Earth, except in composition. Even the asteroids, in some cases, may have subsurface oceans. When we talk about ocean worlds, we're talking occasionally about asteroids. This is not something I ever expected when I went to university that would be discovered in my life. It's getting to the point that our small pale blue dot, this is an image taken by Messenger of our planet Earth and the moon. This is what we look like from space. Our pale blue dot, with all its water on the surface, is basically a showy peacock that is just displaying all the water it's got. But even the least showy of worlds seem to have water. Everywhere we look, we keep finding this stuff. No one would ever call the moon a water world. Do not consider it a water world. The moon is a harsh mistress was probably pretty accurate. You can process the regolith, and in processing it through energy intensive processes, get out water. Depending on where you go digging, you're going to have more or less luck. It turns out that the constant temperature shifts on the surface of the moon caused as it rotates once per orbit. As it rotates, water can get sublimated, heated up, and that process puts it into the lunar atmosphere. And Brownian motion, random motion, causes it to move around. But if the next time it gets cold, it happens to settle down, freeze out of that tenuous atmosphere into the dark part of a crater that stays dark forever, it's going to stay there forever. So we have what are called cold traps on the moon, places where when those random motions lead to water ending up in them, that water is trapped there. And so now the question that we have that we want to send a robot to answer, or a human, but robots, when they die, no one cries as much. I mean, the people operating the robots probably cry, but it doesn't quite become the same headlines, whatever we send eventually. Those cold traps could, like an Apple TV for all mankind episode, have ice built up in the shadows, waiting to be mined. And it's a real question. Is it going to be easy to access or hard to access? Because how that water is trapped there is going to determine how easy or hard it is for life to eventually, well, get to set itself up inside habitats on our moon. And looking across our solar system, one of the great sadnesses is Venus. Somewhere between 300 million and 1.2 billion years ago, the surface of Venus wasn't all that different from the surface here on Earth. And something happened. We don't know what. And the surface literally got resurfaced. The Magellan spacecraft, which 31 years ago arrived at Venus, used a variety of different radar detectors to bounce signals off of Venus and map out the surface hidden beneath the clouds. And there were order of 1,000 craters found on the entire world, compared to the millions we find on Mars and the moon. This dearth of craters is what gives us that 300 million to 1.2 billion years ago, the surface was resurfaced number. Other models have found that the cloud cover on Venus may have originated at about the same time. And up until then, the temperature on Venus was consistent with the same kinds of life we have on Earth. This was once a twin to our planet, another somewhat warmer, water, ocean-covered world. We think, according to computer models, we're going to send more spacecraft out to figure it out. And we don't know what happened. There is new research coming in showing that there appears to have been ongoing volcanism randomly occurring across the surface. And there are also models that say that the planet, which doesn't have tectonics, it doesn't have the crustal plates moving relative to each other, coming apart, pulling together, like we have on Earth. And those models theorize that essentially all the heat inside of Venus built up until there was essentially one massive episode of volcanism that overturned the planet's surface. Our planet can't have that happen. But the thing about 300 million to 1.2 billion years ago is life had started to form on Earth in those periods. And it's possible that this former ocean world may have had life starting to form. And that's part of why people are so desperately looking at its atmosphere today. Because if life started to form, then there's the possibility that as the environment changed, it figured out how to live instead in the circulating cloud currents. That's a different talk, but it's something to think about. And there's water even on Mercury, again, in the shadowed places, like with the moon. Everywhere we look, Ryogu, Bennu, even these worlds appear to have water in their surface. And what's amazing about these two is just how chaotic they are. These two worlds, Bennu on the left, Ryugu on the right, are what happens when you have essentially a dump truck load of gravel and rubbish from an asteroid collision that gets gravitationally pulled together. These are both rubble pile asteroids. It turns out that Ryugu is a bit more solid than Bennu. And Ryugu, fascinatingly enough, appears to be made of pieces of the asteroid Vesta, as well as a variety of other bodies. And this raises a really interesting potential history in our solar system. Ryugu has in it these pieces of Vesta that likely got removed from Vesta when in the early parts of our solar system, 3 to 3.5 billion years ago, something hit Vesta. Something hit Vesta hard in what became Vesta's South Pole. It hit Vesta so hard that Vesta went from being a round asteroid to being an egg-shaped asteroid. And Vesta actually has wrinkle ridges around its equator. It's the only object in the solar system that has its equator geographically mapped out for us. And whatever it was that collided with Venus, it created a massive crater. It deformed the asteroid and it sent shards of Vesta everywhere. There are all sorts of meteorites that have been identified as pieces of Vesta right here on the planet Earth. Some of you may have them. Now, because there's pieces of Vesta just about everywhere, and because the Dawn spacecraft went and visited Vesta and got us even better data on what Vesta looks like up close, the Hayabusa 2 spacecraft that went to Ryugu, it was able to find all throughout the surface boulders and rocks little shiny bits. Those shiny bits matched Vesta, but it also found other bits that matched other families of asteroids. This is multiple bodies that have collided and come back together, perhaps multiple times over the age of the solar system. And mixed in with all of this, they have found bits of, well, minerals that had to form in water. Now, that doesn't mean Ryugu has water today. The answer is still out on that one. We don't know. But Bennu has water. And as the story goes, Hayabusa 2 got to Ryugu first and started flinging things at Ryugu. Hayabusa 2 was a really amazing mission from JAXA where they literally threw everything, including an anti-tank weapon, onto the spacecraft. And then from the spacecraft, threw it onto Ryugu. They created craters. They dropped things that moved around by having springs that flipped them around. They just dropped a whole bunch of stuff onto the surface of Ryugu to explore it. And then OSIRIS-REx got to Bennu. And when OSIRIS-REx got to Bennu, OSIRIS-REx had rocks thrown at it. And the story goes that Ryugu warned Bennu, and Bennu decided to go on the attack initially. That did not actually happen, but it makes for a great story. So Bennu, as the mission approached, they saw fragments floating away from the asteroid, getting shot away from the asteroid. And it's thought that what is happening is there's volatiles, water, frozen carbon dioxide, other ices within the minerals of Bennu. And over time, as it expands in the heat of the sun and contracts, things flake apart. They expose these volatiles trapped in the minerals to sunlight. And the expansion of those gases is enough to fling things off the surface. Exactly how loosely held together this world is not something we really had a good understanding of until the fateful day we attempted to touch the surface of the asteroid. The plan was that the arm of the spacecraft would fly down and touch and bounce off the surface. And in the process of touching, a gas canister was fired that would fling material off the surface up into the collectors. And if we were lucky, we'd catch enough grams of material that we could distribute it to all of our international partners. We really thought the spacecraft was going to bounce. Looking at this series of images, the spacecraft is not seen to bounce off the surface. What actually happened was the arm touched the surface, went through the surface, kept going through the surface, buried itself 0.5 meter into the surface, would have kept going, except the spacecraft fired its thrusters and was able to escape. Had it not fired its thrusters, we might have actually just lost our spacecraft into this gravel pile. What made sense in retrospect is the gravity is so low on this world that all these orange and apple and grapefruit and pea-sized pieces of gravel, the grapefruit ones are held down about as well as your ball pit plastic ball. And Ryugu touching it was the equivalent of trying to step onto the surface of a ball pit. You just fall right in. Imagine that. Gravity's so low that rocks and boulders feel like swimming in a ball pit. Just a whole lot less air because this is an asteroid. And mixed in there is the remains of worlds and collisions and water and everything mixed together. And there's a sample on its way back. And we'll get here next year. And we just have to wait. But there's water everywhere. And now when we look out at our solar system, we know that nothing out there is truly completely dry. Everything is at least in part made of water. And I am now going to answer your questions as best I can. I see one saying, when you talk about water planets, do you literally mean H2O, or are there other liquids you put in that category? I generally mean actually liquid water. Now with Titan, which I apparently left the slide out of, I think I edited it for time because I wanted this to be 45 minutes. So Titan is another world out there. It's orbiting Saturn, and it has methane at the triple point, the way we have water at the triple point here on Earth. So on the surface of our planet, we see water both as a liquid, a gas, humidity, not my friend today, a liquid, a gas, and a solid in the form of ice. Well, you have the same thing with methane as a liquid, a gas, and a solid on the surface of Titan. And there we talk about having methane and ethane oceans and lakes and rivers. In general, most of these places, we think it's extremely salty water. We could be wrong. We will eventually find out. But the temperatures are consistent. The pressures are consistent with it actually being H2O in a liquid form, probably with a whole lot of salts. Salts change the temperature that water freezes at. Salty water freezes at lower temperatures than non-salty water. Do we have any other questions out there?
We have one more. I'm going to kind of rephrase.
Okay.
Rephrase this question. Essentially, he's asking about life developing on other planets. Are there the building blocks of life that are on other planets besides just water that we think is out there, or can you talk about that a little bit?
Yeah. So the general building blocks of life are amino acids and organic molecules, and we find amino acids in interstellar clouds. They're just really big molecules that form naturally when you leave your space gases alone. We are now looking to see what kinds of molecules we can find on Mars and other worlds. We know that Mars has plenty of organic materials. It has everything you need. It also has things that will kill you, like perchlorates. But there's life forms on Earth that care more and less about perchlorates. So extremophiles have a way of figuring out how to survive in all sorts of crazy places. But the universe, carbon is commonly made. It is generated in the majority of stars of pretty much any star will eventually, except for the smallest red and brown dwarfs, will get you carbon. The bigger stars go on to get a whole lot more other stuff created. But that carbon, nitrogen, oxygen cycle, that means that carbon is common and hydrogen is common. Oxygen isn't as common as carbon, but it's still out there, plenty of it. And all these things will, if left alone, form all the molecules. And one of the craziest things to me is we find formaldehyde on a regular basis in outer space. We find alcohols on a regular basis, ammonia on a regular basis. It's all out there. Not a lot of it, but it's all out there. So I see the question, the higher atmosphere of Venus has been mentioned as a possibility for life. Do you know how much water in the atmosphere of Venus, and is that still in the realm of possibilities? So I want to say it was back in February. I could be getting the dates wrong. There was a series of papers that came out, all interrelated, on the possible discovery of the molecule phosphine in the atmosphere of Venus. And phosphine is considered to be a bioindicator, something that in the temperature pressure regime that we find on Venus isn't naturally occurring, but can be a biological byproduct, sort of like methane on Earth is a biological byproduct. Cats, humans, cows, they all produce methane. So since then, the results have been called into question. It appears there is a calibration error in the data, and the phosphine result may not be actually real, or at least with a high enough signal to noise that it's believable. But prior to realizing that there was a problem in the observatory's data reduction protocols, this wasn't the scientists, this was the information the scientists were given to use. Prior to that, it was believed that there is enough water in the atmosphere of Venus to form droplets that are sufficiently large for microscopic life to be able to exist. And more to the point, that the mixing of droplets at altitude would allow the mixing of genetic materials to occur. We don't know what's going on. We do know that there's a haze layer lower down that is consistent with the story of there potentially being a layer where spores could exist. We do know that there is circulation of the atmosphere where large droplets exist at higher altitudes. These ideas have been around since Carl Sagan, since before I was born. And hopefully one of the three spacecraft, or multiple, preferably, of the three spacecraft planned to go there, will be able to answer these questions for us. A lot of modeling is currently involved, but data will be ours someday. Do we have other questions?
I think you kind of answered, there was a couple others, but you answered them just naturally through your talk. I think that's everything we have. Usually right after we let you go, 10 more questions come in. But everybody's probably frantically trying to type something, but as of right now, it looks like that's all that we have. So thank you very much. I'm going to take over the screen from you.
Okay.
Very good talk. Thank you very much. We really appreciate you you speaking to us tonight.
I'm going to go put my house back together after catching a bird. So may none of you have birds in your house this evening.
Thank you.
Okay. Bye-bye.
Otherwise, I will say goodbye to you all. Thank you very much for joining, and we look forward to seeing you all in person next month. Have a good night.